This video is going to go over hybrid orbital theory. You're going to learn a lot more about hybrid orbital theory when you take organic chemistry next semester. And there are other kinds of orbital theories that you may or may not learn about in the future. So we're going to introduce this one, and I'm going to warn you that this is a little bit abstract, but if you just try to take it all in, then I think by the end it will make sense to you. And of course, if it doesn't, you can come and talk to me about it. So we're going to start by talking about covalent bonds. The one type of covalent bond is called a sigma bond, and you see the symbol up there in parentheses. That's the lowercase Greek letter sigma. And so typically we use the abbreviation for the bond, but when you say it out loud, you say sigma. You can just write the word sigma, but that's less common. So what you see here is two hydrogen atoms, and they are going to come together, and their electrons which are housed in 1s orbitals, they're going to overlap, and that overlap is what constitutes the sigma bond. So a sigma bond is when you have head-on overlap, right? So you see that the electrons are between the two nuclei, and so that's going to be what constitutes a sigma bond. We're going to talk about a different kind of covalent bond a little bit later. And so it's what I'm circling here is sort of the overlapping area that we would consider the sigma bond. And we can look at a few other examples of sigma bonds. These would be fluorine atoms that are going to overlap to form an F2 molecule. Now these are p orbitals. Remember that p orbitals are sort of dumbbell shaped. The reason there are two different colors, they're red and blue for each one, is just because those represent two different phases. You probably aren't going to need to know anything about that, but that's why they're two different colors there. And so you can see these two p orbitals are going to overlap, and again you get a sigma bond because you get this head-on overlap where the electrons are between the two nuclei. So that's the sigma bond there. Going to look at, I think, one other one. This is a hydrogen chloride molecule. So here we have hydrogen's 1s orbital, and it's going to share that valence electron with the 3p electron in chlorine. And then you're going to get the overlap that you see there. And so this is the sigma bond here. Now, so these are all just very simple overlap of orbitals that we've already talked about, right? So these are the 1s orbital is where hydrogen's single electron is housed, and then the 3p orbital is where chlorine's valence electron that it's going to share with hydrogen is housed. Now we're going to move on, and we're going to talk about carbon, because carbon is a little bit different than these other guys. And this is where the idea of hybrid orbitals comes into play. So here we have carbon's orbital diagram. You can see that it has 6 electrons, and it's number 6, so that should make sense. We have the 1s electrons, which are inner core electrons, and then we have 4 valence electrons. So you notice here that carbon's 4 valence electrons, 2 of them right now that you see in this orbital diagram are in a 2s subshell, and the other 2 are left unpaired in separate 2p orbitals. Now, one thing that we know from experimental observation is that when methane is studied, the carbon in the center, it's going to share its 4 valence electrons, and it's going to share 1 valence electron with each of the hydrogens that it bonds to, right? You can see that there. Carbon in the middle is the sort of dark gray, and the hydrogens are white. But what we know from experimentation is that the 4 bonds that carbon forms in methane are all exactly the same. So we have to make that make sense with the fact that the 2s orbitals and the 2p orbitals are very different from each other energetically. They have different shapes, they're different distances from the nucleus, and so they're different. But because carbon forms 4 identical bonds, then we have to come up with a theory that meshes with the experimental observation. And so this is where hybrid orbital theory comes into play. So hybridization refers to a mixing of the atomic orbitals to form hybrid bonding orbitals. And those hybrid orbitals are going to all be identical to each other. So what we're going to do is we're going to take the single 2s orbital and the 3 different 2p orbitals, and we're going to hybridize them. We're going to mix them together, and we're going to make 4 identical sp3 orbitals. And we're going to talk more about this sp3 in just a second, okay? But you need to think about this. So 1s and 3p orbitals combine to form 4 sp3 orbitals. So we're going to think about this like a blender, okay? It's sort of like we're making a smoothie, okay? Because what goes in is different and what comes out is all the same. And the amount of orbitals that go in equal the amount of orbitals that go out. And that's also kind of important. You can see that there's a red colored 2s orbital and 3 different lines that are green representing 2p orbitals. And what you get in the end is 4 orbitals coming out. So 4 not identical orbitals go in and 4 identical orbitals come out. So it's just like making a smoothie. So we've got our blender and we're going to make a, it looks like a mango. We're going to make a mango smoothie. We're going to take a mango and we're going to add some milk and we're going to add some ice. And we're going to put it in the blender and we're going to get some smoothies out, okay? So the volume of material that goes in is going to equal the volume of material that comes out, right? And we all kind of understand that. So it's sort of the same idea with orbitals. And what comes out is all identical, right? All the smoothies are the same. So let's look at sp3 hybrid orbitals first. There are 3 different kinds, well, there are 3 different kinds of hybrid orbitals that we are going to talk about. There are 3 different kinds that are relevant to carbon, which you're going to talk about all next year. Carbon is going to be sort of the whole shebang in organic chemistry. So for sp3 hybrid orbitals, we have 3 2p orbitals, the dumbbell-shaped ones on the bottom, and a single s orbital. So there's one s, and there's also one s written in the name sp3, right? So the one s orbital, and there's a one single s orbital here. Now it gets kind of confusing because when I say 1, I mean the quantity 1. This is a 2s orbital. That's just the shell number. That's the principal quantum number. So I'll try to avoid that confusion. There is a single s orbital, and then there are 3 different p orbitals, and they're shown here. So that's why there's a superscripted p, a superscripted 3 next to the p in sp3. And you can just, there's just an assumed superscripted 1 next to the s. Okay, so that's why it's sort of a s1p3 hybrid orbital, because there's a single s orbital and 3 different p orbitals that go into it. And we're going to combine them together, and we're going to make 4 different sp3 orbitals. And so on the right hand side here we see the result of this mixing together, this hybridization process. So what you see at the top is a single sp3 orbital that they're trying to show you what one of them would look like. Okay, so one sp3 orbital shown at the top, and the different colors there, the red and the blue, is the same as what it means on the left. It's just meant to show you different phases of the orbital, which I don't really care that you understand that. That's a concept that sort of goes beyond this class. What you see underneath here, these green sort of balloon looking things, these are 4 sp3 orbitals all shown together now. And so what you have on the left with the 3 different not identical orbitals going in, I'm sorry, 4 different not identical orbitals going in. There's the s and then the 3 different p's. You add those up and you get 4. On the right hand side you get 4, right? So what goes in also comes out. So 4 orbitals go in that are different, 4 orbitals come out that are the same. Okay, so now we're going to move on and we're going to talk about methane. Methane is the molecule that we talked about at the beginning where we have a single carbon and 4 attached hydrogens. So methane forms 4 sigma bonds between the carbon and each of the 4 hydrogens. So if we look at the carbon is the atom we've been talking about all this time, where the 4 different atomic orbitals hybridize to form 4 identical hybrid orbitals that you see that look like the green balloons there on the left. And each of those houses a single valence electron that it's going to share with each of the hydrogens. And the hydrogen, the red spheres represent the 1s atomic orbitals for hydrogen. And so you can see the overlap on the right, and wherever these orbitals overlap with each other, that's where they're sharing the electrons. That represents the sigma bonds. So we have 4 sigma bonds on the right. There's 1, 2, 3, 4, represented by the overlap of the orbitals. And it's a head-on overlap, just like we talked about before, where the electron density is between the two nuclei. So you can see that it's between the hydrogen nucleus and the carbon nucleus in each case. Now we're going to move on, and we're going to talk. So here we have the 3 different molecules when we talked about Vesper theory, and we looked at these 3 molecules very specifically. Because all 3 of them have 4 electron clouds. And so anytime you have a molecule where the central atom has 4 electron clouds around it, that would be emulated by the 4 balloons that we used in lab, then those 4 electron clouds are going to use sp3 orbitals. And you know that that's true because there are 4 electron clouds. If there are 4 electron clouds, then you must need 4 orbitals. And if you need 4 orbitals, then they must be sp3 hybridized orbitals, because that's the only way you can get 4 identical orbitals. We're going to talk about when you need 3 electron clouds and 2 electron clouds in a few minutes, because they form different hybrid orbitals. So each of these 3 molecules is going to have sp3 hybridized orbitals. For methane, it looks just like we saw before, where the carbon has 4 identical sp3 hybrid orbitals. Each one has a single valence electron that it's going to share with the 4 different hydrogens, and their valence electron is in the 1s orbital. Now, ammonia is a little different. It has the 4 sp3 orbitals, but one of the orbitals houses a lone pair. You can see that one is at the top, and the other 3 will bond with the 3 hydrogens, and they will form sigma bonds, where the 1s orbital from hydrogen will overlap with the sp3 orbital from nitrogen. And finally, water, the oxygen has 4 sp3 orbitals. 2 of those orbitals house lone pairs, and the other 2 will overlap with hydrogen's 1s orbital to form 2 sigma bonds, one with each hydrogen. Okay, so now we're going to move on. We've talked about sp3 orbitals. We're going to move on and talk about sp. That if we go back, 3 orbitals go in to hybridize, and then 3 orbitals come out as a hybridized orbitals, as identical hybridized orbitals. So now what you're seeing here, the product of hybridization, is at the very top right you see a single sp2 orbital with the different phases shown in red and blue, and then at the bottom in green are the 3 sp2 orbitals shown together. So the 3 that go in, they arrange themselves in a trigonal planar geometry. We're going to talk about that. But you can see the 3 hybrid orbitals are trigonal planar, and then the unhybridized p orbital is still remaining there. We're going to talk about that in a minute. So 3 orbitals go in, 3 equal sp2 hybrid orbitals come out. So 3 unequal atomic orbitals go in, 3 equal sp2 hybrid orbitals come out. Those are shown in green. And then the p orbital, the single p orbital that remained unhybridized, is still shown there. It's shown in red and blue. Okay, so I've highlighted that there so you can see it. And that's going to be important for the bonding that we're going to look at in just a minute. Okay, so we're going to move on and talk about the bonds that these form on this next slide. So ethylene is the molecule shown here. Ethylene, the 2 black spheres there are carbon atoms. Each carbon atom has 2 attached singly bonded hydrogens, and then the carbon atoms are doubly bonded to each other. So that's a double bond between the 2 carbons. So double bonds mean that you have 1 sigma bond and 1 pi bond. We haven't talked about pi bonding yet. It's a little bit different than sigma bonding. So if we look at, on the bottom, we have the 2 adjacent carbon atoms, and you can see the 3 green lobes are the sp2 orbitals. Those result from the hybridization of an s orbital and 2 different p orbitals. and those go together. So we have two different carbons, and that's why there's two different sets of orbitals there. And then with the unhybridized p orbitals are adjacent to each other, right? You can see that the red lobe and the blue lobe, one goes above and one goes below. And those two carbon atoms, because they are adjacent, they have adjacent p orbitals that are still unhybridized. So these two adjacent unhybridized p orbitals, which are shown in red and blue, they will overlap with each other to form what is called a pi bond. So pi is spelled pi, but I think everybody's familiar with the Greek symbol pi from math. And so pi bonds are a little bit different than sigma bonds. For a pi bond, one pi bond, it has electron density above, up here, and below the plane of the atoms, rather than what we see for a sigma bond where the electron density is between the two nuclei. In this case, the pi bond, the electron density is above and below the nuclei. So the red and the blue that you see on the right-hand side represent one pi bond. So one pi bond has electron density in two places, above and below the plane of the atoms, the nuclei. And then we still have sigma bonds here, okay? So each sp2 orbital, which is shown in green, the green balloons on the left, each of those will overlap. And in the case of the two carbons, they overlap. One sp2 orbital overlaps with another sp2 orbital, and that forms one sigma bond. But each carbon also has two other sp2 orbitals that will overlap with the hydrogen 1s orbitals. Those aren't shown here, but those will also form sigma bonds with the 1s orbitals from hydrogen. The hydrogens aren't shown. I think they're just trying to make it as uncomplicated as possible. Okay, so now we're going to move and we're going to talk about sp hybrid orbitals. And as you might have guessed, with a single s and a single p in the name, we only have one of the p orbitals that's going to hybridize. That means two p orbitals remain unhybridized. And we're going to put the s orbital and a p orbital that you see on the right in a blender, and we're going to blend them together and hybridize them into two identical sp hybrid orbitals. So this s is that s, and this p is a single p. Hybridize. Those going in on the left will form, now it's not showing us the different individual sp orbitals, it's only showing us the two green sp hybrid orbitals together, right? So that's two hybrid orbitals in the middle. They separate at in a linear geometry 180 degrees apart. And so what you see on the right is the unhybridized p orbitals that remain. And so you see the two green balloons, the two green lobes are two different sp hybrid orbitals, and then two orbitals, those two orbitals go in, you get two equal sp hybrid orbitals coming out. And then over here you have these two remaining unhybridized p orbitals. There's one here above and below the plane, and there's one here in front of and behind the plane. Okay. And so these are all sort of 90 degrees from each other, orthogonal. Now, so there's one unhybridized p orbital here, and the other unhybridized p orbital is here. And they're both, remember, they're dumbbell shaped, and so they have electron density in two places. So now we're going to talk about acetylene. It's kind of hard to see here, but that's a triple bond between the two carbons. And a triple bond is a single sigma bond and two pi bonds. And those add up to 3 bonds. That's a triple bond. So now if you look at what we looked, the end of the last slide showed you what an sp2 hybrid orbitals would look like. And this would be two adjacent carbon atoms, just like the two you see at the top in acetylene. So if they are next to each other, then the sp orbitals, the green ones, are going to overlap in a head-on fashion, and they're going to form a sigma bond. Then the unhybridized p orbitals, there's two adjacent unhybridized p orbitals, and there's actually two pairs now. We have one above and below the plane, and then we have another one in front of and behind the plane, sort of coming out towards you and going back into the board. So the adjacent unhybridized p orbitals overlap to form one pi bond each, and since there are two pairs of adjacent unhybridized orbitals, you're going to end up with two different pi bonds, and those are over here. One pi bond has electron density above and below the plane of the atoms, just like in the last example with ethylene. And then there's a second pi bond that has electron density in front of and behind the plane of the atoms. So it's sort of like a cylinder of electron density going around. Now, probably the most important thing for you to be able to do is to identify the hybridization of a given atom. Okay, now this isn't really much different than the things we've been doing so far when we did Vesper theory. All you're going to do, so this table shows you that the number of charged clouds around a central atom is going to tell you not only the arrangement, the sort of electron cloud geometry, but that alone will tell you the hybridization. So if you need two charge clouds, then you must need two orbitals, which means they must be sp hybridized. If you need three charge clouds, then that's going to be a trigonal planar electron cloud geometry, and it's going to have an sp2 hybridization because that's the only way to get three orbitals, three identical hybrid orbitals. And then if you need four charge clouds, that means that you need sp3 hybrid orbitals because that's the way you get four identical bonding hybrid orbitals. So these numbers on the left, you would have done, this is the sum that you would have calculated when you do Vesper theory to figure out the geometry. When you look at the central atom and you count the number of attached atoms plus lone pairs, whatever number you get there is going to be this number here. And another way to think about it is this is the number of balloons you would have used in the lab. Okay, so if you would have attached two balloons to each other, you would have gotten a linear geometry. That means that that central atom would be sp hybridized. Okay, so we'll practice these in class, but let me know if you have any questions about